Hey, so you've got a quiz on rational functions coming up? Perfect. You're in exactly the right place. We're going to build this thing from the ground up, so by the end of this, you'll have everything you need to feel totally ready. Let's get right into it.
Okay, when you first see one of these functions, with the fractions and the x's all over the place, I get it. It can look pretty complicated, but I promise you the logic behind it all is actually super straightforward once you see it. We're just going to cut through the noise and focus on the rules you really need to know.
And this is going to be our motto today. This quote really nails it, right? Our whole goal here is to make this stuff clear and simple, not to get bogged down in confusing details. Every step we take is going to be logical and easy to follow.
So here's our game plan. First, we'll cover what a rational function even is. Then, we'll talk about finding its domain, basically where it's allowed to exist. After that, we'll go hunting for those invisible fences called asymptotes, both the vertical kind and the other types. And finally, we'll wrap it all up with a quick summary that's perfect for your pre-quiz review.
All right, first things first. Before we can solve anything, we have to know what is this thing we're even talking about. Let's lock in the basic definition.
So at its core, a rational function is really just a fraction. That's it. But instead of numbers, you've got one polynomial on top, which we'll call p of x, divided by another one on the bottom, q of x. Now here is the single most important rule of this entire topic, the one thing that unlocks everything else. That denominator, q of x, can never ever be 0. Why? Well, because in math you just can't divide by 0. It's undefined. It breaks math. Just keep that one rule in your head.
And you know what? That big rule about the denominator not being 0? It leads us directly into our next topic. Finding the domain. The domain is just a fancy word for all the possible x values you're allowed to plug into the function. So finding the domain is actually a process of elimination. Think of yourself as a detective. Your only mission is to find the x values that would make the denominator 0, the values that break that golden rule. Once you find them, you just say the domain is everything else. All the other numbers are totally fine.
Let's look at a couple of quick examples. On the left, our denominator is x plus 2. So what x value would make that 0? Well, if we solve x plus 2 equals 0, we get x equals negative 2. So the domain is literally every number in the universe except for negative 2. Simple, right? Now look at the one on the right. The denominator is x squared minus 25. We set that to 0. What number, when you square it, gives you 25? Well, there are two of them, positive 5 and negative 5. So for this function, the domain is all real numbers except for 5 and negative 5.
Okay, now for the cool part. Those numbers we just kicked out of the domain, they don't just disappear. On the graph, they create something called vertical asymptotes. The best way to picture them is like invisible electric fences. The graph of our function will get super close to them, but it can never actually touch them.
Now, for the official textbook definition, a vertical asymptote is a vertical line, like x equals 2 or x equals negative 5, where the function's graph just goes wild. As you get closer to that line, the graph will shoot straight up toward positive infinity or straight down to negative infinity. It gets infinitely close, but it will never cross that line. So, how do we find these invisible fences? This is the best part. You already know how to do it. It is the exact same process we just used for finding the domain. You just take the denominator, set it to 0, and solve for x. The only little catch is you should make sure the fraction is simplified first. The numbers you get are the locations of your vertical asymptotes.
Let's check this one out. The function is already simplified. The denominator is x minus 3. Set it to 0, and you get x equals 3. Boom! That's it! You have a vertical asymptote at the line x equals 3.
How about another one? The denominator is x squared minus 49. We set that to 0 and solve. That gives us two answers, right? X can be 7 or x can be negative 7. And that's totally fine. It just means this graph has two separate vertical asymptotes.
But what about a case like this? The denominator is x squared plus 9. Think about it for a second. Can that ever be 0? Well, x squared is always going to be a positive number, or 0. So if you take a positive number and add 9 to it, there is no way you're getting 0. It's impossible. So since the denominator can never be 0, this function has no vertical asymptotes at all. All right, so we've mastered the vertical ones. But there are other types of asymptotes too, horizontal ones and slanted ones. And what these tell us is the function's end behavior. Basically, they answer the question, what is the graph doing way out on the far left and far right edges as x gets huge?
Now, finding these is a totally different game. It has nothing to do with setting the denominator to 0, so forget that for a minute. For these, all we have to do is look at the degree of the top and bottom polynomials. And the degree is just the biggest exponent you see on any x. We'll call the top degree n and the bottom degree m. That's it. Just compare those two numbers.
Okay, this slide right here, this is your ultimate cheat sheet for your quiz. You just need to memorize these 3 rules. Let's walk through them. Case 1, top row. If the degree on top is smaller than the degree on the bottom, it's the easiest one. The horizontal asymptote is always the x-axis, the line y equals 0. Done. Case 2, middle row. If the degrees are exactly the same, you still get a horizontal asymptote, but this time you find it by making a fraction out of the leading coefficients. That's just the numbers in front of the highest power backs. Case 3, bottom row. If the degree on top is exactly 1 bigger than the bottom, you don't get a horizontal line. You get a slanted line called an oblique asymptote. You find its equation using polynomial long division. But for your quiz, the main thing is just to recognize when to look for one.
Okay, deep breath. We've covered all the main pieces. Now let's pull it all together into one simple final checklist you can use to study. This is your game plan for any problem. Here it is, your 3-step plan to victory. Step 1, find the domain. Set the denominator to 0, find the forbidden x values. Step 2, find the vertical asymptotes. First, simplify the fraction if you can, then set the new denominator to 0. Those answers are your vertical lines. And step 3, find the other asymptotes. Don't solve anything, just compare the degrees. N on top, m on the bottom. Is n smaller, equal, or 1 bigger? Pick the right rule from our cheat sheet and you're golden. That is the entire process.
And that's really all there is to it. It's just a logical process. You know how to find where the function can exist, you know how to find its invisible fences, and you know how to figure out its end behavior. You've got the checklist, you understand the rules, you are absolutely ready for this. Now go ace that quiz.